Welcome, everyone. I am so delighted that you're here today. I'm Erin Gray, the grants manager with NumFocus, and I'm thrilled to be part of this community. I'm so excited to introduce our next speaker, who some of you may know well, but if not, then you're in for a great session. Dr. Chris Rackauckas is the VP of Modeling and Simulation at Julia Hub, the Director of Scientific Research at Puma's AI. You may know Dr. Chris as the co-PI of the Julia Lab at MIT, and also the lead developer of SciML open source software organization. So I'm really excited about this presentation today. I really encourage everyone to please interact in the chat. Let us know if you have any questions, introduce yourself. We're delighted you're here today. So I'm gonna go ahead and turn it over to Dr. Chris.
Yeah, thank you very much for the kind introduction. So what I'm going to talk about today is, as the title says, why Julia's GPU accelerated ODE solvers are 20 to 100 times faster than Jackson PyTorch. Now, I think that the why is what really matters, right? A lot of people look at the numbers and just go, oh, speed up. Just want to talk about like, oh, I don't believe that could exist or anything. But what I'm going to do is I'm going to really go into the why, and we're going to explain all of the milliseconds about where the performance difference comes from. And at the end, you should have a much better understanding of where performance comes from in programs and how we got this performance and what that means about the use cases and everything associated with it. So I hope that, by going into copious amounts of detail, we can really kind of make the numbers make sense. So first, let me kind of give a quick start as to, what we're talking about. So I'm Chris Rackauckas. I build out this SciML open source solvers in the Julia ecosystem. If you come from something like Python, you might understand it as like, SciPy in Julia. It does things like linear solving, nonlinear solving, differential equation solving, optimization, integrals, partial differential equations, right? That space of SciPy. It's a little bit different than SciPy because it also includes, integration with machine learning. So kind of what you would think about as PyTorch and JAX, also things like GPUs, and also the space of things like Modelica and Simulink. So things around symbolic modeling languages, symbolic computing. So things like SymPy are also kind of folded in here for that reason. So it's kind of an expansive organization, but it's around these kind of solvers and the utilities around solvers more generally. This is what we work on. And of course, we have a lot of these papers. In fact, this one just got into ACM transactions and mathematical software, which explains how our new nonlinear solver, so things, things like Newton's method and such, how they're able to be, more faster and more robust on things like battery models and models of chemical reaction systems and spatial and everything, right? So you can see, for example, MinPack being the thing that the Fortran code that is wrapped by SciPy and also sundials in here, where you can see the brand new methods that are, what they're doing. And the paper goes into the whole architecture as to how we're able to achieve that performance. A lot of this comes from mixing symbolic tooling into the solver, something that we call symbolic numeric methods. So that way it can do things like automatic differentiation, but not just automatic differentiation, but also discover sparsity patterns so that it can use sparsity patterns without the user ever having to intervene and give a sparsity pattern. So there's a lot of this kind of tooling that we develop just kind of to give a flavor for what we do. But one of the things that we're really well known for is the differential equation solvers, right? So, this is just a high level overview of some of the results of differential equations.jl. So this is, the non-stiff ODE solvers. You have, for example, R's library for DE solve versus, something like MATLAB and Python. And, you could see that for orders of magnitude, the same solver or the same problem solved to different orders of accuracy, or you're able to see in vertical lines, this performance difference of a few orders of magnitude, right? So we generally say around 50x to SciPy, 50x to MATLAB, 100x to RSD solve, but it can be dependent a lot on the problems and all sorts of things. And we'll go into a little bit of detail there, right? So we have this for non-stiff ODEs. We also have this for stiff ODEs. And one of the things that our organization has gotten really well known for is also not just that it's able to outperform some things from Python or R, but we actually actually build all the solvers ourselves, right? So we have, these direct comparisons against things like CVODE and the Fortran codes, right? And we're able to show that, some of these new methods like Rosenbrock methods can outperform, even when you're going directly against the Fortran methods, because, so there's a lot of things that we do in terms of new methods. So it's not just implementation, also things around new methods, and especially methods that are designed to exploit new details of hardware that were not exploited in the methods that were created back in the 80s and 90s, right? So that's who we are. But I think, even just to start, just to get in the right framework, I want to kind of go into the reasons for performance on these ODEs. Because people kind of look at this and just go, okay, 50x, 100x, this is JIT compilation, or people just kind of throw one term out there. But I think that if you actually sit down and try to think about performance, you can actually understand what's going on. So let's do that just for a simple ODE, right? So here I'm looking at the Locke-Volterra model. So this is actually all pulled from a paper in Nature Methods called Julia for Biologists. If you're curious about all the details, you can dive into that. But here's one graph from there, right? So this is a Locke-Volterra equation. It's a non-stiff ODE of just two equations. And we can see, for example, the performance of Python, MATLAB, and R as kind of one grouping right here. These are like the high-level languages. And then you have the C and Fortran solvers directly, right? This is kind of this middle language performance. And then we have the new methods within Julia, right? Again, the main difference here is things around modernizing implementation and also just new methods, right? Vern 7 is more efficient than methods like DP5 and things like that, right? And so there's new methods, but there's also gaps due to implementation. In fact, there's a large implementation gap here, right? And so, and then the question people always have is like, oh, what if I use Numba, et cetera, et cetera? Well, let's actually just go directly into that, right? So this is the Locke-Volterra equations, right? There's 8 scalar operations as part of the code. And now in Julia, right, what ends up happening is you effectively only have, you effectively will fuse a lot of these function calls into a single thing, because at the compiler level, it'll do something called inlining, where it wouldn't call functions. It would actually just directly put in the lower level primitive that it needs to do within within the code, right? So instead of having function calls and function calls and function calls, you can decrease that stack of function calls by using this kind of inlining that is done within the LLVM compiler, right? And if you use like something like Numba, then you will also get that as well. So what you do with Numba is you can take take this F function that you would send to the ODE solver, you JIT compile it, and then you send that to SciPy and you say, okay, now run my ODE on this F, right? And if you don't do that, then you have 8 function calls that all have to go back to the Python interpreter, right? And so if you just kind of count it up, you just see, okay, a function call in Julia costs about 5 nanoseconds. A function call in the Python interpreter takes 150 nanoseconds. Now, if it's Numba, you call a faster function, but you still have to call that function from Python, right? So if you actually then count it up, right? So there's a difference in the way that the Julia functions are written. So the Julia ODE solver functions are mutating an array. The ones in SciPy, they're actually computing a new array. The time to allocate that array in Python is 300 nanoseconds. Each floating point operation is just 2 nanoseconds, and there's 8 of them, right? And then count up the number of function calls. If you just do this back of the envelope calculation, you can see that, this is what we would expect the timings to be: about 20 seconds, 1,500 seconds, about 4,000 or 450 seconds. If you actually then time it on your computer, it's almost exactly what you expect, right? So what I'm meaning to show here is that, like the fact that we get this order of magnitude difference, like you can actually understand directly where that comes from, right? So using Numba inside of SciPy is slower than Julia, which is hitting 20 nanoseconds instead of 425 nanoseconds, because 300 nanoseconds of that is from the allocation of the array that comes out, and about 150 nanoseconds of that is from the Python interpreter, right? So again, if SciPy is actually running in Python, but then the ODE solver is actually written in Fortran, what it's actually doing is sending that function into the Fortran code. But every single time it calls your F function, it hits the Python interpreter, and then it has to go into the NumPy thing, right? Or Numba thing. And so that's where that 150 nanoseconds come from. And so you can see exactly there that, there's 2 principles then. You need to design libraries around being mutating if you want to get the maximum performance on CPU, and you need to design your system so that way you don't have this interpreter overhead at all, which can be difficult for high level for things that take in high level functions. So things like optimization libraries, things like differential equation libraries, right? If the user is actually passing you a function, it could be pretty hard in a lot of high level languages to get rid of this top level function call. And this is one of the big reasons for an implementation difference in Julia, specifically in the space of differential equations and optimization, right? Now, if you're doing something like neural networks where you're just calling kernel calls, then the user's never actually writing a function that's given to the system. You're using a lot of built-in functions. This effectively doesn't exist, and the allocation time is kind of decreased because, and I'll go into that in a little bit, and so you don't have as much of a difference. But in this domain of differential equations, you see this pretty huge difference, and it's pretty easy to explain just by reading off exactly where the timings come from, right? So I want to do this now in the context of going to GPUs. But the real idea then is that choosing the right parallelism for ODEs depends on the problem. So let me first kind of get into this in a problem-dependent way before I get into the main result. So there's three different ways that you might want to parallelize an ODE solve. If you have a big set of ODEs, so think of partial differential equation, you want to parallelize within your solve, right? So within that ODE that you're solving, you want to parallelize the operations of it because they're just large enough to be parallelized. So PD discretizations, large reaction networks, parallelized within the solver. If you have a small ODE system, then you actually don't have enough parallelism to do. Think about like parallelizing the Lorentz equations, right? There's just arrays of three things. Parallelizing three things at a time doesn't give you anything. What you can do is you can develop methods that give you more parallelism, things that are solving parallel in time, right? They're less efficient methods, but they are methods that naturally just have more computation that can happen at the same time. So it is less computationally efficient, but could be faster if you're exploiting the right hardware, right? And then there's a third set of problems, which is the one that we'll be talking about in the results against the machine learning libraries, which is the ensemble case, where you have the same ODE that you're solving with many different parameters. So say you're doing a parameter sweep over a space, right? For that kind of case, what you would do then is you say, okay, I have this one set of ODEs, and boom, I solve it parameter 1, 2, 3, 4, parameter 10,000 all at the same time, right? And this is a very embarrassingly parallel kind of problem over the space of ODEs, which are kind of non-parallelizable because they're kind of stepping through time, right? So you can try to parallelize them by doing parallel in time kinds of things, or if you have a large enough system, you can parallelize in space. But all three of these cases require different ways of doing the parallelization. So I want to kind of cover the two of them really quickly before I get into the ensemble case. If you have large ODE systems, then what you want to do is you want to say, GPU parallelism. What you want to do is you want to make sure that your state or your initial condition lives on the GPU. You want to make sure that all the solver internals are on the GPU as well, which means all the broadcasts that are going on inside the solver and all the linear algebra has to live on the GPU. The user's function, right? Remember that F that I told you about. The user's definition in the ODE also has to be written to work on GPUs, and then the solution just needs to stay on the GPU. If you satisfy all those, then you do pretty well for the large ODE case, right? So this is what PyTorch and JAX will also do this effectively. The Julia solvers have this, but also even a lot of other codes like sundials and C++. They have a way of using an array, a GPU-based array that you can write operations on. For anything that's like the large ODE cases, this is what when people say I have a GPU compatible ODE solver, they generally mean that they support this specific case, right? Now there are some cases for which this works well, and some cases for which this doesn't really do all that much, right? The key thing to really keep in mind is, to think about what happens for why the machine learning libraries end up being efficient for machine learning, but not necessarily for a lot of scientific computing, comes down to the fact that you have that O of n cubed operations are so much in the computation that you can ignore other things. So what I'm showing here is the difference between allocating operations versus non-allocating operations on GPU and CPU. You can see that for O of n operations, like this is like a broadcast or a map expression, this is the optimized way of this is the unoptimized way of doing it versus the optimized way, which is broadcasting into an already allocated array. You can see that the memory cost of an allocation is actually scales like O of n. And so it's always faster to do the array allocations correctly. And here you can see the difference between the GPU one or the CPU ones and the GPU ones. GPU is not even faster until you get a large enough matrix. O of n squared kind of ends up in a middle case. But O of n, what you see with O of n cubed operations is that the cost of doing the allocation versus not doing the allocations effectively zero once you get to large enough matrices, right? And so when you think about like these codes that are optimized for GPU computing, something like PyTorch, right? What they're really relying on is the fact that when I do machine learning, I'm doing a lot of big matrix multiplications. These are O of n cubed. And so a lot of the computational details around the user doing memory management, the user doing manual SIMD doesn't actually matter. And that's why these are fast. But if you're in the space of actually doing a lot of O of n operations or O of n squared operations, then that assumption is actually not correct, right? And so it means that applying some of these machine learning libraries to some of these cases will give you some suboptimal results. And one way to actually understand this then is that if you're using implicit method solvers for ODEs, right, these that naturally have dense linear algebra in the LU factorization. And so doing this array, I have big arrays, so let me put it on the GPU. That will end up doing pretty well if your linear algebra is using things like cuDSS and whatnot. Then implicit solves will do pretty well on GPU once your ODEs are sufficiently large. That's not necessarily true for explicit ODEs because they're all O of n operations. You might get like a 2x, 3x speed up, but you don't get that magical, the GPU is 10,000 times faster, because when you're only doing O of n operations, a lot of the memory operations, a lot of the kernel call overhead actually starts to matter a lot. And this is something that we'll see in the Ensemble case as well. So this is just to go over, like when a lot of people talk about GPU accelerated ODE solvers, a lot of times we're talking about this case. The Julia solvers handled this. They do just about the same as a lot of the other codes, because in this case, everyone has the same architecture for how they're doing the parallelization. For small ODEs, this is kind of a topic that we talk about separately. For the sake of time, I'm going to kind of jump over it. We have different methods like extrapolation methods that can solve for different DTs at the same time. Then there's special parallelizations, things you can do, yada, yada, yada. It ends up being faster for only small ODEs. So for example, systems of 5 to 10, 200 ODEs, it ends up being the fastest stiff ODE solver by about 4x, because it's a specialized stiff ODE solver that is forcing you to have more parallelization. But once you get to large enough problems, it turns out that the parallelization within your BLAS library starts to kick in for the LU factorization, and the multi-threading there is just fine. And so that ends up not being any faster, right? So for small enough ODEs, there are even tricks you can do on CPU. But now then the last thing is for ensembles of small ODEs. What are the kinds of tricks that you can do specifically on GPUs, right? So the key thing here is that if you're to say, okay, I'm going to take a machine learning library and I want to make this work in a way that is doing, GPU accelerated kernels for an ODE solve, right? The first thing that you can really come up with is the idea of, well, I do have this thing over here, right? I have this idea that if I have a large enough set of ODEs, I can put them into a GPU array and I can just do GPU operations on every step of the call, right? And this is effectively what the machine learning libraries will do when they approach an ODE solve, right? They say, hey, look, I have a PyTorch based ODE solver. I can GPU accelerate it. And if I want to solve a bunch of the same ODE for different parameters, I can just, instead of having my initial condition of 3 things, I can have initial conditions of 3 by n, where I'm just solving n versions of that same ODE at the same time. Now I have big enough kernels to put it onto the GPU, right? And so it's basically using some approach where you just say, I have this ODE. Now let me turn every operation into an array of, the value of x for every different parameter, the value of y for every different parameter, and run all those simultaneously by using GPU arrays over that whole space. So I convert the problem of solving the same ODE with many parameters into a problem that is just one giant ODE. And then I use this technique right here, right? You should start to probably already kind of trigger something in your head to say, well, is it actually efficient to shove my way of solving this problem into this form, right? But if you just put VMAP on an ODE solver that's written to be JAX compatible, that is effectively what you'll get, right? So I think a lot of people think about it as like VMAP is a thing that gives you parallelism. It's not that it gives you parallelism; it gives you a very specific form of parallelism that is generating larger kernels for using GPU operations, right? But then the question is that the right way to do parallelism for the ensemble problem, right? Um, Now let's take a look at this same case here, right? So you had this Locke-Volterra equations, right? And again, you have 8 scalar operations. Now, if you turn this into something where every single operation is now like, instead of just looking at, oh, I have X, I have Y, you now have X for every single ODE that you're solving at the same time. So X is an array, GPU array of all those ODEs solved, and Y is a GPU array of all those ODEs solved, right? And what ends up happening here is you have, say, 8 scalar operations, right? So you have to do, operation of X times Y, and then a scalar times it, and each one of these calls ends up being a kernel call to the GPU. Now, if you're using something like PyTorch, it might all be a different kernel call. If you're using something like JAX, it might fuse some of these kernel calls, but still, you're doing a lot of kernel calls in every single call of F, right? Now, the other thing that you can imagine is, what if I took my entire ODE solve and generated a CUDA code for that entire ODE solve that is specialized on it, right? If you did that, then you'd only do one kernel call for the entire ODE solve. And then the question is, how much of a performance difference would you get from that? Well, it takes about 5 to 10 microseconds in order to do a kernel call on the GPU. So we just calculate it out, right? So if this F call takes 8 kernel calls, right, and it takes 5 microseconds to launch, then and every single step of an explicit ODE solver method takes actually 5 F calls. Then what you end up having is at every single step has an overhead of 28 milliseconds. You do that for solving, you do that over 1,000 steps of the solve, you're at 28 seconds versus 5 milliseconds. Right there, you can already kind of instantly see what the difference is. So if you were if you're to take this VMAP approach and say, I'm going to generate all my calls to be, every step of my thing to always be doing GPU calls, the problem is then you have a lot of GPU calls, and a lot of these GPU calls are all O of n. And so then you're spending a lot of time doing kernel call launches. And so you end up having a lot more overhead versus something where you build a specific kernel. You basically write a CUDA kernel specifically only for that ODE. You compile it, and then you only do one kernel call launch to solve the entire ODE. If you get rid of that overhead, then boom, there's where your 1,000 times performance difference come from. Now, JAX ends up doing a little bit better than this because it can kind of do some kernel fusions in here. So it's not doing 8 operations. But this is then the idea that it's still doing, one of these operations 7 times per step, 1,000 steps versus just literally one time through the whole solve, right? And this is how we actually end up at this result here, where you have that the Julia solvers ends up being much faster than the PyTorch and JAX methods, right? Because it's not that we're just all using GPUs. We're using GPUs in fundamentally different ways, where what we're doing here is we're generating a kernel specific to this GPU. We're compiling it, and then we're running. We basically call that kernel with all the different parameters, and what we get back is the entire ODE solve from one GPU call. Versus the machine learning based approach, which the machine learning libraries are effectively doing every single step of the code, and every O of n operation is doing one kernel call, getting the GPU array back, one kernel call, get the GPU array back, and that overhead from the kernel calls adds up. In fact, one of the ways that we're able to kind of prove that this is the case is that we actually have implementations of the Julia solvers in Diffie GPU using the other approach. And we end up at about the same performance as JAX, right? So we're able to just show that it is inherent to the approach of how the parallelism is being designed that gives you this performance difference. The other thing that you can see from this is that there's a library that was written directly in CUDA, where the user has to give their ODE as a CUDA kernel, and then it will compile it in a similar way that we do. And you can see that we get about the same performance as that. So it's a design decision to the way that the parallelism is designed that gives you this 20x to 100x performance difference because of the kernel call overhead that's going on, right? And now you go, again, why is this kernel call overhead something that you don't care about as much in machine learning? Why is PyTorch able to be fine for machine learning? Because it's really focused on O of n cubed operations like matrix multiplication, whereas what happens with the VMAP here is it's doing a lot of O of n operations, and those are just not as efficient on GPU. They end up having a lot of kernel call launch overhead. And so what we then able to do is we're able to say, well, as long as we can generate kernels for different devices, we can do this on CUDA, OneAPI, AMD GPU, and also Apple Metal devices, and get really slick, really optimized codes for this specific case, right? Now, it does mean that we have limitations, right? We need to be able to make sure that the entire ODE solve lives within a kernel, which means you need a sufficient register space. So this only works for ODEs up to size 200 or so. So there's limitations that come from the design. But if you're doing something like looking at a chaotic system of less than 200, of less than 200 ODEs, like for example, the Lorentz equation, doing a parameter sweep is literally 100 times faster if you take this approach. Um, and then this also applies to stiff ODE solvers. You can see that here's the stiff ODE solvers that have a kernel generating approach versus the JAX ones as well. And you can see that there's this similar 76 to 130 difference due to the way that even in this case, you might say it's a stiff ODE solver. So it does have a bit of the O of n cube operations, but it ends up being a batched LU factorization instead of being just a full LU factorization. And so it's just not able to be as efficient as a full O of n cubed kind of case. Now, one of the things that you might find interesting in here, though, is SODA is actually a CUDA kernel that is written directly for solving stiff ODEs, and we're able to outperform that quite a bit as well. And that comes down to the fact that we're using a different ODE solver than what you'd expect to use for this case. And for this equation, actually, some of the BDF methods end up being some of the most efficient. But it turns out that the methods that are efficient for CPU are not necessarily those that are efficient for GPU, because if you always force a fixed amount of work, then if you don't have a fixed amount of work, like a Newton method, then on GPU, you might need to run all iterations of that Newton method, whether it's required or not, just because different warps might require that. And so moving to a less efficient method might actually be faster on GPU just because it's ideally built for the hardware. We go into that in a lot more detail inside the paper, but this is actually why even though that this is a handwritten GPU CUDA kernel, are the ones that we're generating out of Julia are much faster by a few orders of magnitude, because there's also a method difference, and that method actually matters for the hardware. So you have to think about both at the same time. But does this apply to other problems? It turns out that we built, for example, global optimizers using the same idea. Particle swarm method, where we put the entire particle swarm on GPU, where it's doing different parts of the particles at the same time. It has all this kind of stuff. You can read about this here as well. Again, it's compiling the entire optimization to the GPU and running the whole particle swarm there to be able to cut down on kernel call overheads and get that same major performance improvement. So the conclusion is that performance is not just a number, right? And I think everyone just likes to say like, oh, it's 100 times faster. No, but like these are not just numbers. You can know exactly where the performance difference comes from. And when we talk about GPUs, you really need to use the right parallelism model for the right problem. Just because you're using a GPU doesn't mean that you're using the GPU in the correct way for your problem. And a lot of these machine learning libraries in particular, they only generate GPU parallelism in one way. And that one way is not necessarily efficient for all ways that you might want to parallelize. And I think that this project really kind of highlights that there are other ways that we might want to be using GPUs, and we really need to consider the architecture for how you use GPUs if you really want to get that maximal performance. So yeah, thank you. Hopefully by the end of this, now everyone understands why we are faster, right? Not just that the Julia tools are, but this is why. So thank you very much. And I see a few questions here. Yeah. So Julia aims for both high performance scientific ML and computing. How does Julia compare to Mojo? So the main thing with Mojo, right? So the main thing with Mojo is that Mojo doesn't do a lot of the optimizations directly, right? Mojo gives you a syntax for being able to write out SIMD arrays and things like that. And so when you actually want to optimize your optimized code looks a lot like Rust, actually. You have to write down all the types. You have to write everything into SIMD vectors. You have to, manually SIMD everything. The Julia code actually is exactly, it's high level code, just kind of retargeted. So, Julia in the end ends up looking a lot more like Python in the optimized form than Mojo, which I find looks actually a lot like Rust once you've done all the optimizations. I would say check out check out the blog post about optimizing Mojo for BLAS operations, and that will kind of describe in detail. Once you see the code at the end, you'll see that it looks a lot more like you're writing like lower level LLVM type of code. And there's a reason why, and we could go into details there. How does Julia compare to building code and say in Fortran, skipping over Python? Yeah, so I think the Julia is still a high level language, right? Something kind of looks like Python. Now in Fortran, there are a lot of array constructs and things these days. In general, Fortran does get a little bit more optimization than Julia because Fortran does not allow certain forms of aliasing, and that can help the compiler get a few more optimizations. But the Julia programming language has a much higher level, in which case sometimes allowing the compiler to do more for you can help. In fact, so this project, for example, right? The user actually gives us an F function written in Julia, and we are able to retarget this to .ptx CUDA kernels automatically in a way that can be kind of difficult in some lower level languages, right? Because we want to say, give me the math and I'll reinterpret it into different implementations. Whereas when you go down to something like C or Fortran, you're more naturally writing down an implementation rather than the high level math, right? Julia kind of sits in between the two spaces nicely. But I mean, there is something lost. With Fortran, you actually get more aliasing optimizations automatically. So in Julia, if you want to get the same SIMD, sometimes you have to do the IVDEP operation. You have to manually tell the compiler to IVDEP because it's not able to prove the anti-aliasing. So when you're writing your own BLAS libraries, when you're writing your own linear algebra, that is the one thing you have to keep in mind in Julia that you might not have to do in Fortran. I mean, so if I understood, depending on model size, you said you change your parallelism. Yeah, exactly. So I'll go back to that point. So depending on your model size and the applications, you actually have to change the model of parallelism. Julia does not offer an advantage over here. In fact, I think the fastest one still in the space is sundials. We're behind. We're about 75%, 80% of the way there. So for the large ODE systems on GPU, sundials and Julia are kind of close, but sundials is a little bit faster. For small ODE systems, we have a lot of novel methods, but they mainly are just for ODEs. It's really difficult to make small ODEs parallelize well on GPUs. For ensembles of ODEs, then we have this special trick that gets us an extra 100x in this case. But yeah, it depends on your use case how you're going to parallelize. Can you explain a little bit more detail why Julia has zero allocations in the example that I give? Yes, let me actually go to the documentation. I can just show you exactly what this looks like. So if I go to docs.sciml.ai, and then we look at the differential equation solver here, right? So I'm going to pull over to this tab in a second here. So if you look at the differential equation solver, you go into the first tutorial, right? You then go down here. So here's the Lorentz equation, right? Now you write down this Lorentz equation. Notice the funny thing about the way that the differential equations are written in Julia is that there is no array that is returned from this function, right? Instead, what's happening is you have the array u that comes in, and the derivatives are written as a mutation to this input array. There's no array that's created, right? If you look at something like the SciPy ODE solver, they tell you to create an array as the output that is the derivative, right? That right there is the array that is being allocated. So what this Julia solvers do is they actually have a pool of memory, and they require that the user directly writes into that pool of memory rather than creating new memory. And that is exactly where that allocation comes from. It's a high-level design decision for the library that then has this performance effect. Now, I will say that Julia tools are not the only ones that do this. The underlying Fortran tools, most of them actually have an interface like this. So when SciPy actually writes the interface over the Fortran tool, they then expect the user to create an allocating function that returns an array, and then they do the in place right into the Fortran code. And so that overhead of the 300 milliseconds or 300 microseconds, right, is just part of the SciPy design. So when you end up having some other libraries that are trying to do optimizations in Python, right, they tend to move the JIT compilation and such to a different level, and they go around the SciPy solver because of this design in there. And there's trade-offs in either way, right? By requiring the user to write this in a different way, they have to be pretty careful about what they're doing, right? If you allow mutation on arrays that can be an unsafe operation in some cases, but in some cases actually required for performance. So it's kind of it shows you that some of these things around we mutate we have a 4-argument syntax where we mutate, and then SciPy has one where we return the array. It's not an arbitrary choice. It's a design choice about flexibility, speed, and what users expect, high levelness and whatnot, and it reflects in the actual performance you get out. Yeah, I think that covers all the questions in the chat. Yeah. yeah, and I could definitely happen jump into the Discord, and also say that if anyone wants to chat about any of these details, we're talking about topics like this all the time, especially in the Julia Slack. So this Julia Slack has 15,000 people or whatnot who like to talk about performance of code. So if you want to just scan this QR code and jump into the Slack, I'm happy to go into copious amounts of detail into I cut out all the flame graphs and everything. I could have gotten into a lot of more detail, but I think that this is a high level enough detail where someone can start to understand what things are thought about when trying to build performant methods for these cases. But again, happy to go in more detail anytime. Just show up at the channels. So thank you very much.